Hey, Dr. Clark coming back at you with another preview video. This time we're looking at Chapter 9, Multiple Means, and in particular, we're looking at Section 9.2, a theory-based approach to multiple mean inference. So this topic is usually called ANOVA, which is short for analysis of variance. That's the kind of test we do when we do more than two means, when we're comparing more than two means. In the same way that we did the chi-squared test for multiple proportions, we do an ANOVA test for multiple means. Okay. Now, the mean group difference statistic we used last time in the simulation-based approach, that does not work as good for a theory-based method. So if we're going to transition to theory-based methods, we need a new improved statistic from the mean group difference, and it's called an F statistic, and it has an F distribution. It's similar to the chi-squared statistic in certain ways, but when we have quantitative data, we get an F statistic. Okay, and the key difference between the mean group difference and the F statistic is the F statistic incorporates sample size and the sample standard deviation in particular, and that's very important. So the mean group difference just looks at the difference between the averages of each group, but it doesn't factor in the standard deviation, so the amount of spread within those groups, and that's going to be an important factor when doing ANOVA testing. Okay, now the F statistic, there is a complicated formula. We're not going to use it. We're not going to need it. The shorthand is that we look at the variability between groups divided by the variability within groups. Okay, now when we had the T statistic earlier with only two groups, when you do x bar 1 minus x bar 2, that's telling you how far apart are the two groups, and then that square root of the standard deviation formula here gave you a sense of the variation in the situation. And that's going to be similar to what's going on. We'll have a way to sort of compare how far the groups apart, how far apart the groups are in relation to the spread of the groups. So that's kind of heuristically what's going on. All right. The example we're going to look at is we're calling ambiguous prose, which we saw before, but this time we're going to make a slight change on it. Okay. And the situation here is when the researchers did the study, they not only said rate your own sense of your comprehension, they actually had the participants recall details from the passage. And then they counted how many details they could correctly identify, and it could be somewhere between 0 details all the way up to 12 details, right? And so if they could recall more details, that shows that they had better reading comprehension. And so in the data here, remember, this group, they read the text, but they never saw the picture. This group, they saw the picture before they read the text, and you can see that they're recalling more details. And then this group saw the picture after they read the text. And you can see the none group had an average detail recollection of 6.6. The before group had an 8.2, and the after group had a 5.37. So you can see there is some difference in these means here, but you can also see the standard deviations are given there, and they've, so we'll use that information when we do the test, the ANOVA test. Okay, so what are the hypotheses for this test? Well, the null is that all three of the long-run mean recall scores under the different conditions are the same. So the average scores of the recall, so there's no association. Okay, that looks like all the mu's are equal to each other. Remember, quantitative data, so we're looking at averages here. The alternative is at least one of these mu's is different, okay? And you could write that out just saying, at least one of the mean scores is different. Or there's an association between whether and when they saw the picture and how many details they were able to recall. So that's kind of the standard hypothesis system. There are validity conditions when doing ANOVA. You want to have 20 in each group. That's similar from when we've had quantitative data before. If you don't have the 20, then you probably don't want to have either outliers or skew, but having 20 in every group, it makes the validity condition pretty well. Well, essentially what that's doing is it's making sure that the null distribution matches up with the theoretical null distribution that we would get when doing this F statistic test or ANOVA. But this is a new one. We've never seen this before. Equal variation. The guideline is we don't want the standard deviations to vary very much. Okay, and if you go back here and look at our data, you'll notice this standard deviation is 2, this one's 1.8, this one's 1.4. They're all pretty similar, okay? And if there was too much difference in the spreads, that could be a problem. All right, so the idea here is that we want the standard deviations to be similar to each other. One guideline is the smallest one or the largest one is no more than twice the smallest one. So if the smallest standard deviation is 2, the largest standard deviation should be 4 or less, right? So you don't want the largest. If the smallest standard deviation was 3 and the largest was 10, well, that's a problem because then you've got too much difference in the variation. All right. The ANOVA test, we can run it in the applet. You just paste in the data. It gives you the dot plot here, gives you the summary statistics. And if you change it from mean group difference to F statistic, it'll compute the F statistic for you, in this case 12.67. So 12.67 is like a measure of how far apart are these groups from each other, and that's measuring the level of association between the conditions. Okay, and then we plot the null distribution. Again, we select F statistics to do a theory-based test. If you click this box, it will overlay the theoretical distribution. You can see the simulated F statistics are lining up perfectly with the theoretical distribution. That's because those validity conditions are met. So it's the theoretical distribution is more or less right on top of the simulated null distribution. And then you can see our F statistic was 12.67. When you put that in, there is nothing as extreme or more extreme as what we got in our sample than when we did it randomly. And so that's evidence that we have an association between these variables. Our p-value is 0, both from the simulation and the theoretical p-value right here. So that's how you do the actual inference on the applet. Paste in the data, do either a simulation or a theory-based test, selecting F statistic like so. So what do you conclude? Well, we've got a small p-value, so you can reject the null hypothesis. The null hypothesis was that all of the averages were the same. Those parameters, mu1, mu2, mu3, they're all the same. So at least one might be different. If at least one is different, which one is different? Well, you can do a follow-up confidence interval test by clicking a button in the applet, and it'll give you the 3 confidence intervals comparing after and before, comparing after and none, and comparing before and none. And you can see that all 3 are significant because they're highlighted with an asterisk. None of them include 0. So an interpretation would be something like, okay, you can see the before minus none is between 0.5 and 2.8, basically. So seeing the picture before leads to an average comprehension between 0.5 and 2.8 points higher than never seeing the picture at all. That's, we're 95% confident that on average, people who see the picture before will have 0.5 to 2.8 points of recollection higher than the average of those who never saw the picture. That's the kind of sentence we're looking to construct when we interpret these confidence intervals. All right. So we'll obviously get to more details in class. That's the main gist of what we're doing. But we've seen that shape of that F distribution is that skew right. Okay. And everything's positive because of the way the F statistic is computed. Strong evidence means a big number that's far to the right. We saw those validity conditions of having 20 in each sample, and then the standard deviations not being too far away from each other. And then how do you use the applet to run the ANOVA? Well, we've kind of seen the applet printouts there. It's basically just putting in the data and hitting go. And then those follow-up tests give you the confidence intervals. Anyway, that's the main ideas for section 9.2. Hopefully that gives you a little bit of idea what we're going to do, and then in class we'll hit a bunch of the details. So we'll see you then.